Hello everyone, welcome back to Indian Chemistry A session, and once again hearty welcome to Vignan University. So already we interacted during the bridge course time, but this time I'm going to introduce actually main course, Indian Chemistry A course, and it is actually designed for particularly CIC and IT students. So let us see the details. The main objective of this course actually, it is trying to cover the importance of chemistry and its applications in engineering discipline. At the same time, Indian Chemistry A course trying to cover trying to provide some fundamental knowledge and some of the basic science concepts like chemical bonding, water technology, electrochemistry, batteries, nanomaterials, etc. kind of things. So that means from this course you can able to learn all these topics, and that knowledge actually useful for the even next year, in future purpose. Okay, so let us see the contents of the Engineering Chemistry A course. So Engineering Chemistry A course mainly consists 5 different units. Unit 1 actually chemical bonding and water technology, Unit 2 actually electrochemistry, and Unit 3 actually batteries, and Unit 4 instrumental techniques for chemical analysis, and Unit 5 nanomaterials. So like this, Engineering Chemistry A course actually covers various topics like this, starting from chemical bonding to the most advanced topic like nanomaterials. So in order to cover all these topics, you have to go through the following reference books like this, reference textbook like this, like chemical bonding and physical inorganic chemistry textbooks for the covering the chemical bonding concept, and water technology can be covered by Indian chemistry topics, and electrochemistry you can use this textbook, and for instrumental techniques you have to follow this textbook, and for nanomaterials you have to follow advanced nanomaterial textbook like this. So all these books actually available in our library. You can go to the library, you can get all these books actually. Okay, so today I am going to start Unit 1, that is chemical bonding and water technology. If you see the contents involved in the case of chemical bonding water technology, basically 2 concepts are there in the first unit. One is actually chemical bonding, and the second part actually water technology. So I think you have some idea about the water technology because we have already discussed some topics in the bridge course time. So we discussed about what is hardness of water and types of hardness, and we already discussed about determination of hardness of water by using irradiated titration method during the bridge course time also. But today I am going to focus on the chemical bonding concept. So in the case of chemical bonding, we have 3 different topics like this, and in the case of water technology, we have 3 different topics like this. If you finish this topic, that means after completion of this topic, what is the outcome? So the expected outcome from the Unit 1 actually, so upon completion of the Unit 1, students will be able to understand or apply the knowledge of crystal field theory or molecular orbital theory to the various type of chemical compounds. In addition to that, students were able to analyze various water samples, and they can check the quality of the water, and they can able to design the suitable water purification mechanism in order to convert the various impure waters into the soft water or fresh water kind of thing. So this is the expected outcome from the Unit 1. So now let us start the Unit 1, chemical bonding and water technology. So today I am going to focus only on chemical bonding concept. So we will see the water technology in the later sessions. And again, among these 3 topics, today I am going to start crystal field theory of octahedral and tetrahedral metal complexes. Okay, so in this case, we are going to deal with the various octahedral and tetrahedral metal complexes. So then the question actually, what is metal complex? So we have to understand what is metal complex. Once you understand what is metal complex, we can able to understand about what is octahedral metal complex, what is tetrahedral metal complex, and their formation and their reactivity and their application, all those things. So let me explain what is metal complex. So metal complex actually, this is one of the coordination compound in which there is a central metal atom or ion. There is a center metal atom or ion, and that is bonded to 2 or more number of ligands. That is actually bonded to 2 or more number of ligands. You can see here. So in this view, you can see there is a central metal atom that is represented in yellow color, and that is bonded to 6 number of ligands in this manner. So that is bonded to 6 number of ligands in this manner. That means it is one of the octahedral metal complex. So this is actually example for the octahedral metal complex. So like this metal complex always consists one central metal atom, and that is surrounded by 2 or more number of ligands. And the geometry of the metal complex mainly depends on the how many number of ligands are attached to the center metal atom or ion. So depending on the number of ligands attached to the metal center or bonded to the metal center, so we have different geometries for the various metal complexes in this manner. So you can see here, in the first case, the central metal atom or ion bonded to 2 ligands like this. So in this case, the geometry actually linear geometry like this, and we can represent by using this manner, ML2 notation like this. And in case if metal atom bonded to 4 number of ligands like this or like this, we have 2 different geometries like this. So this is actually a square planar geometry, and this is actually tetrahedral geometry. So that means in the case of 4 ligands are attached to the metal center or bonded to the metal center, we have 2 different geometries. Either square planar geometry is possible or tetrahedral geometry is possible. That is mainly depends on the nature of the metal center and the surrounding ligands only, the strength of the surrounding ligands only. And in case of 6 ligands are bonded to the center metal atom or ion, there is a octahedral geometry like this. So like this we have a various geometries for the different types of metal complexes, and the geometry of the metal complex mainly depends on the how many number of ligands attached to the metal center and nature of the metal center and nature of the surrounding ligand, etc. kind of thing. So that means each type of metal complex actually having their own properties like color property, magnetic property, or optical property, or reactivity or catalytic activity like that. So we have to understand all these things by considering by seeing the bonding involved in that cases in those complexes or the formation of metal complex, all those things we have to discuss. So this is something about the metal complex, and I want to discuss a little bit more about the octahedral metal complex. Okay, so this is the representation of octahedral metal complex. We have to represent by using ML6 notation like this, and we can also represent octahedral complex in this manner also. So here this is actually central metal atom, and that is bonded to 6 number of ligands in this manner. So here L actually ligand. L means actually ligand. So ligands are actually nothing but these are actually neutral molecules or anionic species. Basically they can able to donate pair of electrons to the metal center. So always ligands means ligands are actually electron donor species or electron rich species. So they can able to donate that pair of electrons to the corresponding metal center. So depending on the type of ligands we have, we can able to classify ligands into 2 different types, like neutral molecules or neutral ligands, or anionic groups or anionic ligands in this manner. So this is one of the broad classification. So there are number of examples are there for the neutral molecules. For example, ammonia molecule is one of the neutral molecule because this nitrogen center contains one lone pair of electrons in this manner. Similarly, water molecule also acting as one of the neutral ligand because so this oxygen center contains one lone pair of electrons like this, and even CO molecule also acting as one of the neutral ligand like this. And coming to the anionic ligands, and these are some of the examples for the anionic ligands. X minus, so X minus means halide anions like F minus, Cl minus, Br minus, I minus like this, or cyanide anion Cn minus, or nitrate anion NO2 minus, SCN minus thiocyanate anion, and hydroxide anion like OH minus, or even carbonate anion like this. All these are actually examples for the anionic ligands like this. So we have so many other examples also there. So these are some of the examples. So like this, ligand means always electron pair donor. So some of the molecules actually having lone pair of electrons, and some of the groups actually having negative charge. So they will use either negative charge or lone pair of electrons in order to make bond with the corresponding metal center. And coming to the metal center, so this is actually called central metal ion, and this central metal generally belongs to either D block element or A block element. So basically in most of the cases, metal complexes having central metal ion, that is mostly belongs to either transition metals or rare earth metals like this. The reason actually, in the case of transition metals, the outermost electrons are actually enters into the d orbitals like d1, d2, d3 like that. Or in the case of rare earth metals, the outermost electrons are actually enters into the f orbitals. So in the case of transition metals, we have actually either empty d orbitals or partially filled d orbitals, or in the case of rare earth metal also we have a empty f orbitals or partially filled f orbitals. That means they can able to receive more number of electrons from the ligands like this. So that is the reason. So most of the cases, transition metals or rare earth metals are ready to form actually corresponding metal complexes depending upon the type of metal we have, depending upon the type of ligand we have. So, okay, so like this, always there is a formation of metal complex whenever if we combine the suitable metal center with the corresponding ligand. Okay, I will give one more example like this. So this is actually hexaamino cobalt 3 trichloride complex like this. This is one of the important example. So in this unit, we will discuss this example several times. That is the reason I am going to take this example only. So this is the representation of the corresponding metal complex in this manner. There is a central metal atom here, that is actually cobalt 3 plus, and this ammonia molecule acting as one of the neutral molecule or neutral ligand, because what is the structure of ammonia? Nitrogen actually bonded to 3 hydrogens in this manner, and this nitrogen also having one lone pair of electron like this. So this lone pair of electron, it can donate to the any metal center. So that is the reason ammonia molecule acting as one of the neutral ligand like this. And always we have to represent coordination sphere by using square brackets like this. So coordination sphere actually contains complex cation or anion like this, and outside this coordination sphere we have a counter anions. In this case, the coordination sphere actually having +3 charge like this, because we have a neutral molecules and whatever the charge available on the metal center, so that is actually belongs to this coordination sphere. Outside the coordination sphere we have a counter anions like this. We have a 3 Cl- ions in this case. So this is all about actually metal complex and what is ligand, what is how it is how to classify the ligands, all those things. Okay, so in this chapter we are going to study the bonding involved in various metal complexes. So how to explain the formation of some of the octahedral and tetrahedral metal complexes by using crystal field theory. Later we will discuss about the molecular orbital theory. But before that, I would like to show you some of the important characteristic features of these metal complexes. Okay, so now importance of transition metals and their metal complexes what is the importance of transition metals and their metal complexes. So we know that coordination compounds are actually having unique characteristic features, like transition metals can exhibit variable oxidation state. So most of the transition metals actually having variable oxidation state. They can available in +2 state, +3 state, +4 state like that. So depending upon the number of electrons available in the d orbitals and outermost s orbitals. And similar, then another point actually, transition metal ions can form colored complexes. If you see color of the various metal complexes, most of the metal complexes are actually colored in nature. For example, potassium permanganate, purple in color, potassium dichromate, K2Cr2O7, orange in color, like this. These two simplest example. So this is actually one of the tetrahedral moiety, these are also one of the octahedral moiety like this. So basically these are the two different examples. Most of the time we are using in our laboratory, but like this. So here we have a manganese metal center, here we have a chromium metal center like this. So like this, most of the transition metal ions can form colored complexes whenever they are introduced into the water medium or aqueous medium, any other solvent medium. So that is one of the important point. And transition metals can form various coordination compounds. So already we have seen the various geometries of the metal complexes. So depending on the number of ligands attached to the metal center, we can able to generate different types of coordination compounds or metal complexes. That is one of the important features of the transition metals. And fourth point actually, transition metal complexes are having variable magnetic moment values. So most of the transition metal complexes are actually paramagnetic in nature or ferromagnetic in nature. Some of them actually diamagnetic in nature. So depending upon the number of unpaired electrons available in the corresponding metal complexes, so various metal complexes are having variable magnetic moment values. And fifth point actually, transition metal complexes are having unique structures. So this point also we discussed. So we have different types of geometries like octahedral geometry, a tetrahedral geometry, a square planar geometry, a linear geometry, etc. kind of things. So transition metal complexes having unique structures. So due to their unique structure, they have different properties. So that is another reason. And most of the transition metal complexes are actually acting as a very good catalyst for the various organic reactions like palladium catalyst or platinum or silver or copper or iron, nickel. So various metals or metal complexes are actually involved in the various catalytic reactions. They are actually having both industrial importance as well as for the they are actually very much importance towards the research also. So like this, these are some of the important characteristic features of the coordination compounds or transition metal complexes like this. So that is the reason we want to study these type of metal complexes. But at the same time, so what is the relation to these compounds and engineering stream? So is there any engineering applications from these coordination compounds? So let us see some of the important engineering applications from the coordination compounds. Okay, and these are the two different bromine complexes, and this is actually one of the specially designed ligand. And you can see here this chromium actually is surrounded by 6 nitrogen centers like this. 6 nitrogen centers like this. Even in this case also, this is one of the specially designed ligand, and both are actually having octahedral geometry only. So these are actually called polypyridine chromium 3 complexes, or developed particularly for the non-volatile memory device applications. So they are useful in the case of making non-volatile memory devices. So examples for the non-volatile memory applications actually like pen drive or hard disk or compact disc. So in these cases, in order to improve the storage capacity, a transfer of data, so we need actually coordination complexes like this. So that is one of the engineering application. And another thing actually, so here you can see this is one of the specially designed platinum complex. So what is this molecule actually, this group? This is actually C60, fullerene. So this is one of the nanoparticle. So we already discussed during the bridge course time. And this is actually attached to one of the organic ligand like this. And this is also one of the ligand. And this is also one of the ligand. And this is center metal atom like this. So the specially designed platinum complex useful for making artificial light harvesting system. So light harvest system means, so this is the system, it can able to absorb light energy, and that is converted into some other form of energy. So in those cases, this particular complex acting as a photosensitizer. So normally in the case of plants, we can see photosynthesis method. Photosynthesis method. So what is the photosynthesis method? Plants actually absorb sun radiation and converting that into chemical energy, yes or no? So that means plants can absorb sun radiation or light radiation, and that is actually converted into corresponding chemical energy like this. In a similar fashion, even this metal complex, platinum metal complex, acting as an artificial light harvesting system. So in the case of artificial light harvest system, so here you can see, so what is the meaning of artificial light harvest system like this? So artificial light harvest system actually having super absorbing ring in this manner. Super absorbing ring in this manner, and this is the incident photon, that means sun radiation actually falling like this, and this super absorbing ring actually absorbing sun radiation and storing that into another form of energy. But this super absorbing ring actually contains this platinum compound like this. So this super absorbing ring actually made up of this platinum ring like this. So that is one of the important engineering applications, this one. And another example actually, So here you can see some RM complex like this, specially designed RM3 complex like this. So this is one of the specially designed ligand. These are acting as one of the ligand. So this RM3 complex particularly developed in order to make organic light emitting diodes like this. So nowadays, most of the smartphones or any smart device always having OLED screens only, like this. So in order to get better resolution, better graphics or better color mixing, always we need actually OLED screens. So for making OLED screens or flexible OLED screens like this, we have to use some of the metal complexes in this manner. So this is also one of the important engineering applications. And last one actually, here we have a cobalt to bis terpenoid complexes like this. This is one of the specially designed cobalt complex, and this is mainly useful for making resistive memory devices. So what is the meaning of resistive memory devices? The best example actually ReRAM device like this, and these ReRAM device actually one of the storage system, but it can store energy by using charged metal atoms only. So normally memory system normally depends on the electrons. So but this system actually uses charged metal ions in order to store the energy and to transfer the memory from one main memory to the random access memory. And so like this we have to develop some other complexes like this. If you see the diagram of this one, it is actually having so many components like this, but among those one of the component actually there are two electrodes that are available like this. In between the two electrodes we have to introduce charged metal ions in this manner by making complexes like this, and we have to introduce into the two electrodes. So this system actually receiving the signals and converting that into data, and that data can be transferred from main memory to the random access memory even without power sources also. Okay, so like this we have a plenty of engineering applications from the coordination compounds. Okay, so these are some of the examples. So that is the reason if we want to develop any new coordination compound with required applications, required desired properties, always we have to study bonding involved in those complexes. So this is all of the first session. I'm going to stop at this point, and the next class we will see what are the theories are available, chemical bonding theories are available in order to explain the formation of some of the metal complexes. Okay, so thank you one and all for watching this session. If you have any queries, please send a mail to my email ID, or you can also contact to my mobile number also. So thank you one and all.